Today, we are going to break down a classic physics problem. And in the process, we're going to uncover a hidden force that shapes everything from the weather to, believe it or not, the path of a speeding train.
So let's just start with a question that, well, it kind of seems to defy common sense. Imagine you've got this massive 2,000-ton train. It's moving perfectly straight. So why on earth would it be pushing sideways on its rails with a huge amount of force? I mean, there's no wind. There's no curve in the track. What's going on? The answer, it turns out, is one of the most fascinating concepts in physics.
To really get to the bottom of this, we're going to walk through problem 1.116 from Irodov's famous book, Problems in General Physics. Now, if you've ever taken a tough mechanics course, you already know this book is legendary for being difficult. But don't you worry, we're going to break it all down step by step.
So here's the plan. We'll start by just laying out the problem. Then we'll get into the real reason for this whole mystery, the fact that the Earth is spinning. After that, we'll meet the invisible forces that are actually doing the pushing. We'll solve for that sideways force. And then, for fun, we'll figure out how to make it disappear completely. Sound good? Let's get started. All right, first things first, we have to really understand the problem. Before you can even think about finding a solution, you got to know exactly what you're working with. Okay, here's our setup. We've got a 2 million kilogram train. It's at a latitude of 60 degrees north. It's moving at a pretty steady 15 meters per second, and it's going straight along a meridian. Now, that's just a fancy way of saying it's heading due north. Our job, figure out that mysterious sideways force. And now we get to the most important piece of the puzzle. The secret here isn't something on the train. No, it's about the very ground it's traveling over. Just think about it for a second. We feel like the ground is perfectly still, right? But we're all living on a giant spinning ball. For most little things in our everyday lives, we can totally ignore that. But when you have something as massive and as fast as this train moving over a huge distance, the Earth's rotation, it starts to have very real, very measurable effects.
So in physics, we have a name for this. It's called a non-inertial reference frame. You see, Newton's famous laws, like F equals ma, they were designed for systems that are not accelerating or rotating. We call those inertial frames. But our frame right here on Earth is definitely spinning. So to make those laws work from our point of view, we have to add in a couple of extra forces. Sometimes you'll hear them called fictitious forces, but that's a terrible name. They're not imaginary at all. They're just a direct consequence of our moving point of view. Okay, so let's actually meet these invisible forces. First, you have the centrifugal force. And then, the star of our show today, the Coriolis force. Let's break these two down real quick. Centrifugal force, well, that's the outward push you feel when you're on a merry-go-round. It acts on everything just because you're in a rotating system. It all depends on your position. But the Coriolis force, that one's different. It only shows up for objects that are already moving inside that rotating system, and it pushes them sideways. And that is the force that's pushing our train.
And here's the math that describes it. The Coriolis force is calculated using something called a vector cross product. The formula is force equals 2 times the mass times the cross product of the velocity vector v and the Earth's angular velocity vector omega. Now, the single most important thing to remember about a cross product is that the final force is always perpendicular to both the direction of motion and the axis of rotation.
So how in the world do you find the direction of that force? Well, we use the right-hand rule. Now listen, this is a classic spot where students get stuck. You're supposed to point your fingers in the direction of the velocity, that's north. Then you curl your fingers toward the Earth's rotation vector, which also points north along the axis. You see the problem? You can't curl them, they're parallel. So here's a much simpler way. Just remember this. In the northern hemisphere, the Coriolis force always deflects a moving object to the right. So for our train, which is going north, the force has to point east. Easy.
Okay, that's enough theory. Let's get our hands dirty and actually calculate this thing. It's time to solve for that sideways push. Let's get all our numbers in one place. We've got the mass, we've got the velocity, we've got the Earth's angular velocity, which is always the same, and we've got the latitude. We have everything we need.
So to find the size of the force, that vector cross product equation simplifies quite a bit. All we really care about is the piece of the Earth's rotation that's perpendicular to how the train is moving along the surface. And that part is determined by the latitude. So the formula for the sideways force becomes 2 times mass times velocity times the angular velocity, all multiplied by the sine of the latitude, which we call phi.
And when we plug all of our numbers in and punch it into the calculator, we get 3,800 newtons. That's 3.8 kilonewtons.
That's actually a really big force. It's like having 4 large adults constantly pushing on the side of that train.
And, just like we figured out with our little shortcut for the right-hand rule, this force is pointing east. For a train that's going north, east is to its right. So what does this mean in the real world? It means the train is constantly grinding against the right-hand rail, causing more wear and tear on that side of the track and on the wheels.
All right, now for part 2 of the problem. And this is a really fun little physics puzzle. Can we actually make this force just go away?
The question is this. Is there some special direction and some exact speed the train can move at, where the total inertial force, which is the Coriolis and the centrifugal forces added together, just completely vanishes? So the logic here is all about balance. If we want the total inertial force to be 0, it means the Coriolis force and the centripetal force have to perfectly cancel each other out. That means they need to be the exact same size, but pointing in opposite directions. Now, we can't change the centripetal force, but we can change the train's velocity to create a Coriolis force that is its perfect rival. Okay, so the centrifugal force is always pushing outward, away from the Earth's axis of rotation. That means we need to create a Coriolis force that points inward to fight it. So let's use our right-hand rule again. What direction do you have to move in the northern hemisphere to get a force pointing inward, towards the axis? The only way to do it is to travel from east to west. And what about the speed? Well, after you set the formulas for the 2 forces equal to each other and solve for the velocity, the answer you get is about 420 kilometers per hour. Now that is incredibly fast for a train, of course, but it's the exact speed you'd need to go to perfectly cancel out those inertial forces at that specific latitude. Okay, let's wrap all this up. Let's go over the big takeaways here and see how this one little train problem actually applies to some much, much bigger things. So what have we learned? Well, first off, that crazy sideways push on the train wasn't a mystery at all. It was the Coriolis force, a totally real, totally calculable effect of living on a spinning planet. Second, this force doesn't just affect trains. It deflects any object moving over a large scale, and its direction all comes down to that all-important right-hand rule. It's an invisible force for sure, but with very, very visible consequences.
And that leads me to my last question for you. If this force is strong enough to shove around a 2,000-ton train, what else is it doing out there? I want you to think about giant hurricanes, massive ocean currents, even long-range missile trajectories. Every single one of them is being guided by the exact same invisible Coriolis force that we just explored today. Pretty cool, right?